We needed a way to recycle all the metal scrap in our DIY machine shop, so we developed several functional DIY foundry designs that let us recycle our own metal parts into bars that we can reuse on our CNC mill. Our ultimate goal is to see if we can easily melt copper because it has a much higher melting temperature than aluminum. Our plan is to make a very simple process to build these using 3 easy steps. 3D print the mold, fill up the mold with a few things, and start melting metal scrap into brand new blocks of material. Before making the full-size version though, we made a smaller replica just to make sure we got everything right. All we had to do is 3D print this file and fill up the mold. By the way, you can download this file for free on our website, which is listed in the description. The print turned out really well using a Creality 3D printer, so we're ready to fill it up now. We start with some plaster of Paris, which cost just $9. We got some sand, which is dirt cheap, some measuring cups, a mixing tray, and a mixing tool that we just had lying around. The plaster instructions call for 1 cup of water for every 2 cups of plaster powder, and that's what we're going to do. After we add these 3 cups in the container and mix them, we're gonna add in the sand, mix it, and then pour it straight into our mold. Now we haven't really worked with plaster before and noticed that mixing with this tool left a bunch of lumps in the mix. We found that mixing by hand works much better, but do us a favor and leave a comment if you know the best way to properly mix this stuff. Now we cut the sandbag open and added it into the mix. We didn't measure a specific amount into this miniature test foundry, but we will in the big one. We honestly just kept adding sand until the mixture was almost saturated with it. Now we're ready to pour this mixture into our mold. We found that after pouring the liquid in, since it's so viscous, it doesn't flow to the bottom very well. So if you lightly bang the mold on the table, all the air bubbles from the inside will escape to the top. Next, we top it up and make sure we level the top to then get a flat bottom. Then we let it sit for half an hour until it hardens, and meanwhile we take the time to clean up a little. Luckily, this stuff comes right off with water if you clean it before it hardens. Now it's all hardened, so we're ready to remove it from the plastic shell. A quick note, this print is just 3% infill, which means that the inside is almost all air, so it should be very easy to break off. You can see here just how soft the mold is. Prying away at the plastic didn't seem to be easy nor efficient. We also tried to use pliers to rip it apart, but that still required way too much effort. Don't forget, our goal is to make a process which is as close to effortless as possible, so we decided to try a new method. Heat up any thin piece of metal, in our case a scraping tool, and then use it to cut the plastic into pieces. After doing that a few times, the plastic peels right off. However, using this method for the inside was a little tricky, so we needed a new tactic yet again. We found that heating the plastic with a torch of course melted it, but also made it peel right off the plaster. This made it very easy to remove the mold, and it's also the best method to use as we move on to the big foundry. This obviously generates a lot of fumes, so we did it in a well-ventilated area. The finished foundry looked awesome and was ready for its crucible. We picked up this tiny graphite crucible on Amazon for just $8, which fit almost perfectly, but it'll do for our testing. The flame enters from the built-in hole that was present in our mold, and for a flame we're using a simple propane torch that we picked up at Home Depot for $35. We do want to take a second though and just show you the full-size crucible that just came in from Amazon. It's a really good size and I hope it works on our big foundry that we'll show you later in this video. So we fired it up for the first time to see what happens. After about 5 minutes, our crucible was getting red hot, which is perfect. However, a time-lapse reveals our first issue. The plaster totally got consumed by the heat. Now our crucible was still becoming red hot, so it's not the end of the world, but we can't just ignore these melting walls. So we got back to the drawing board and thickened the walls of the small crucible foundry. We call this the medium foundry. We also added 2 more holes for torches so we can crank up the heat and hopefully melt copper. Despite the small foundry working rather well, the extra heat from 3 torches instead of 1 would be good because, well, it's minus 20 degrees out here. So here's the medium foundry. You're looking at the final mold design with the 3 holes. When the print was done, it looked awesome. Again, we get our safety equipment, plaster, sand, large mixing container, and a paint mixer on a drill to save my skinny arms from working too hard. So you know the drill from here on. We added water, powder, and sand into the mixing bucket. The sand is used as a filler and an aggregate with a higher melting temperature. Now mix everything together and eliminate lumps. Pour into the mold. Shake the mold to remove any large air bubbles. And once it's hardened, use the torch to safely extract our medium foundry from the plastic mold. The medium foundry looks awesome, and as you can see, relative to our small design, it's much larger for the same size crucible. We can hopefully expect it to last much longer. Now let's invest in 2 more propane torches from Home Depot. You can also get these on Amazon for super duper cheap. We just had to make sure that the nozzle is the same size or smaller than our original to ensure it fits in the foundry's holes. Alright, setup time. We lay down an aluminum pan and fill it with rocks to act as insulators from the ground, just in case. After we drop the crucible back in, we add a single torch and wait for the crucible to turn red hot. Our first test was a piece of scrap aluminum tubing. Whoa! We were genuinely blown away when this actually worked. Check out that molten aluminum. We were curious if the foundry could consume the entire length of the tube, and it did in under a minute. We now have an entire crucible of molten aluminum out of a $15 foundry and a propane torch. So let's grab our little graphite ingot mold and see what we get. This is probably one of the coolest tools we've ever made. We can't wait to try it on a larger scale. But we have yet to see if it can melt copper because we have lots of electrical wire to recycle into blocks that we can then shape on our DIY CNC machine. Alright, while that's cooling off, let's reset and throw some copper inside. We add a second torch since copper has a melting temperature nearly 2 times higher than aluminum. Our first test will be some copper scrap that we have left over from a part we machined on our DIY CNC machine. Check out that video up here. Meanwhile, I wanted to demonstrate that the outer wall of the foundry stays cool to the touch, which means that our design is working perfectly as intended. Unfortunately, 45 minutes in, the copper was still solid. This was most likely due to the freezing temperature outside rapidly stealing the heat away from our foundry. So we shut everything down and walked over to the bench to examine the aluminum, which was successful. We can totally make a huge block of aluminum to use on our CNC. So up next, we start building our biggest and final foundry. By the way, note how this tiny crucible gets consumed over time. It was a nice solid block at first, and now it's very powdery to the touch. Apparently this is a very well-known fact about pure graphite crucibles, so when we purchased a larger crucible, we got something made of graphite carbide silicon, which apparently doesn't break down with use. It was about $18 on Amazon. As a last note, look how this medium foundry maintained its shape during use, unlike the small foundry. Clearly the thin walls are no good when using plaster, so we're gonna try concrete as well in a bit. Alright, back to building our big foundry. We added 2 extra holes in our design to accommodate the extra torches, and this time decided to print it with just 1% infill to cut on printing time. We also decided to try using HIPS instead of PLA plastic. HIPS is a soluble plastic that should completely dissolve away in the solvent called D-limonene. We're hoping that by submerging the entire mold in this stuff when the foundry is cured, the plastic will just dissolve away so we don't have to use the propane torch method. As always, we start with a small scale test in a jar, and for our test piece, we printed a nice little reminder for you out of HIPS, so don't forget to subscribe. We filled the jar up with D-limonene and let it sit overnight. This worked beautifully, but warning. D-limonene has a bunch of warning labels on it, so it's definitely a dangerous solvent. Luckily for us, after trying to print our part, it totally failed anyways. It turns out that HIPS is as hard to print as ABS because it warps like crazy and we got layer separation as well. So seeing as our printers can't do it, we scrapped the idea and just used our trusty old PLA filament. The print was so big though that it wouldn't even fit in our biggest printer bed, so we had to cut it in half. Then we realized, if we're already cutting it in half, let's just cut it into 4 parts for our viewers out there with really small 3D printers. As always, we're making these designs available for free on our website, so make sure to check that out. And so here are our 4 parts. Evidently, we ran out of PLA mid-prints, but the colors don't matter anyways. You get the point. Now we use superglue to attach the parts. We spread the glue on the outline of the pieces to prevent any plaster from seeping into the cracks. Then we combine and clamp them together and repeat for all 4 parts. You can also use tape if you want, but it didn't seem to make a difference for us. After 10 minutes, we connect the 2 halves together the same way, and when it's done, we have a nice huge mold for our big foundry. Luckily, Creality reached out to sponsor us with this amazing CR10 Smart Pro, which was able to print this huge mold in a single print. We don't need 2 molds though, so we're gonna give this one away to 1 random subscriber, so make sure to subscribe. Now, back to the video. Our mixing ratios for this foundry were 9 cups of plaster, 4.5 cups of water, and 5 cups of sand. Again, mix, mush all the lumps, pour into the mold, and bang it to eliminate the air bubbles. Finally, once it's topped up, just level it with any straight edge. Now while the plaster was curing, it felt very warm to me, so we pulled out our super cool thermal imaging camera and found that indeed, it heated up and was now roughly at my body temperature. We use this as an indicator to determine when it's ready to be demolded. After an hour, we came back to this, where you can clearly see that it's now cooled and cured, so we're ready to demold it with our propane torch method. When we removed the mold, we noticed a huge air gap that we failed to fill, which sucks, but this is just the second insulating well, which doesn't even heat up as seen in our previous test where I was able to touch it, so it's really not an issue. Now let's unpack the big crucible, place it inside, and then add the torch. We're also going to add the second torch and let the crucible heat up for a few minutes. In the meantime, I'll drop this aluminum ingot we made with our medium foundry inside the crucible. We'll know when the crucible is hot enough when the ingot melts into molten aluminum. But even after half an hour, it just wouldn't melt. We know this torch can melt aluminum because we did it earlier, so this foundry is most likely just too big for the heat output per unit time of this torch. We tried using the FLIR 1 Pro again to see if we could see any leaks, but everything looked fine. We also tried to use our medium foundry as a lid to retain heat, but 10 minutes passed and we still had zero luck. But the flame is still at the same temperature, so what's going on? Well, a great example can be shown here. Which one of these do you think will melt the ice cubes first? This cup of boiling coffee or a tub of room temperature water? We conducted the experiment under an infrared camera for a better visual of the temperature change. Well, the coffee has a much higher temperature, but there's very little of it. The water, on the other hand, is relatively colder, but since there is much more of it, it carries far more thermal energy overall. So the coffee starts hot but cools down super fast. The water starts at room temperature but cools off much slower. As you can see, the ice cubes in the water have melted much faster than the ice cubes in the hot coffee. The same thing happens with our foundries. The butane still burns at the same temperature, but the big foundry requires far more thermal energy per second to increase in temperature. When speaking of torches, this energy output is usually measured in BTU per hour. Our current torches are only rated for 3000 BTU per hour. So we went on Amazon and purchased 2 of these 27,000 BTU butane torches for only $19 a piece. We were really impressed with the energy output. So we fired these all up and the amount of heat coming off was far more noticeable. So we threw in our large crucible as well as our aluminum ingot and we gave it about 5 minutes to heat up. Opening it up reveals a successfully melted aluminum part. So now we can throw in a bunch of random aluminum scrap, like these leftover parts from our CNC machine, or even short leftover sections of 80-20 extrusions which melted right down. We also wanted to recycle this entire aluminum tube, so we made small cuts in it, which helped us break it more easily, and we slowly turned it into a gourmet molten aluminum soup. It melted super fast, it took maybe a minute or so, and also topped up our entire crucible. So we're ready to pour into ingots now. Instead of using the graphite mold again though, we're going to use a much larger stainless steel tub. Let's turn the propane torches off first and then pull out our crucible. Pouring the aluminum was super duper easy. So while our blocks cool off, let's clean the crucible and start heating up some brass. We found whatever random brass parts we had laying around and started throwing them into the crucible. We had no idea at this point whether this would work or not, but brass has a melting temperature of 930 degrees Celsius, which is much closer to copper at 1085 degrees Celsius. So if we can melt this, it would be a very good sign for our ultimate goal. We patiently waited and kept on checking the brass, and even though it took 30 minutes, we were super happy when we finally saw that pool of melted brass. So let's find more brass parts to top it up. We got our bigger torches now, so we don't need these guys anymore. And, well, of course, all that plastic on the handle decided to burn and make fumes, but hopefully that doesn't contaminate our final pour. So we tossed in some final scrap parts, and shortly after we had half a crucible full of molten brass. Now it's time to cast it. So we originally decided to use the graphite mold, but last minute changed our mind. As it turns out, that was a terrible mistake on our end. Apparently our brass was so hot that it melted the stainless steel. I still can't explain this one to you, but please take our mistake as an opportunity to learn to use a thicker container and have a tray or something underneath as protection. Our aluminum tray luckily saved our floors and helped prevent a disaster. Once it cooled, we attempted to extract the brass, but it was in there for good. This thing was not coming out. So despite all the parts that went into making this molten brass pool, we had to give it up. As an appropriate replacement, we purchased this ingot mold online. It's 1 centimeter thick cast iron. Now we know that people may be wondering whether it's possible to use concrete as a cheaper alternative to plaster. Well, we decided to give it a try. First though, we made a final design with a much smaller form factor and hence the plug will be much smaller to print. When the 3D print was complete, we grabbed a mixing tub and went shopping for some concrete. At Home Depot, we found this massive bag for just a little over $3. As a little reminder, we used proper safety before starting to measure out the concrete. We've never worked with concrete before, so we're going to use gloves as well. We now measure the amount of water as per the mixing instructions on the bag and we get straight to work. Mixing honestly wasn't super fun and we're not sure what consistency is proper, but eventually we decide to take the risk and just stuff it into the mold. And the process of packing was definitely more fun. Anyways, we filled and packed the mold and then flattened the top with some aluminum pipe. Then we decided to add these screws to the base to act as feet, which will hopefully allow for some ventilation down below. And that's it, we leave it for 24 hours to harden. Once it fully hardened, we proceeded to remove the plastic shell, which was much easier since there weren't two insulating walls to dig down between. For the inside, we kinda just hacked away at it and removed as much as we could with pliers and then just lit up the foundry to melt the rest. This worked really well. With the foundry ready, we put the crucible inside and while it was warming up, we prepared some of our scrap copper. We have a bunch of this wire that we need to get rid of, so we're really hoping this works. We also threw in the scrap copper pieces that we previously failed to melt with our smaller foundries. We waited about 25 minutes, which I would say is a really long time, and we were now ready to pour it into our molds. But of course, the foundry wasn't hot enough to melt all the copper inside, and we were left with this tiny stream of molten copper instead. So we threw it all back into the foundry for closer to an hour and hallelujah, that did the trick. We can officially scrap our own copper into bars to use in our DIY machine shop. So while we let the bar cool down, we cleaned out the crucible to prepare for the next batch. While the crucible was reheating, we decided to extract the copper bar and we were super excited. The copper looked amazing, so we repeated everything with our big cast iron ingot mold. This time it worked so well, so again we let it cool off and then brought it in to compare with our smaller block. I also want to quickly mention some extremely dangerous safety concerns. First, to speed up the cooling of the metals, we would use water. When the spray bottle took too long, we just dunked the entire mold in a bucket. Once it cooled off, we were ready to extract the copper bar. Or so we thought. For some reason, it was stuck to the inside of the mold. We ended up managing to get it out after a long time by banging it on concrete, but it ended up ripping a piece of the cast iron out with it. Perhaps it was too hot when we smelted it? We don't know, so we recommend for anyone smelting copper to use graphite molds instead. This is where we want to emphasize a serious safety concern. Please listen carefully so you don't make the same mistake we did. After we smelted the copper, we decided to recycle all the brass shavings from our CNC machine operations. We filled up the crucible, took it over to the foundry and fired it all up. Everything was looking good to this point. But when we came to pour it into our graphite mold, we did not consider that we had just dunked it in water. And as it turns out, graphite can absorb a lot of water. And what happens when you pour molten metal on a bit of water? Well, it turns to steam and pops. We kept pouring and noticed that the molten brass was bubbling a little more, which means there was probably still water inside. After letting it cool, we realized that some of the molten brass went flying right towards us and hit Dave's safety glasses. This is a great reminder that you should always use all proper safety equipment, including blast shields, proper smelting aprons, gloves, etc. This is definitely extremely dangerous stuff to play with. This water issue was more evident with aluminum, which was bubbling like boiling water. You can even see the steam come out, which indicates the presence of water in or on the mold. This resulted in all our ingots looking really bad, so we decided to remelt all of them and try again doing it properly by driving away the moisture in the mold first before pouring in the molten metal. To do this, we just placed the mold over the top of the foundry instead of the cover for about 5 minutes. By the end, if we turn the lights off here, you can see that it is red hot, which is a good indication that all traces of water have been eliminated. Now we grab the copper that we've been heating for over an hour, and voila, a perfect pour. We also managed to do the same thing with brass without it popping in our faces, and then aluminum. Not all our projects always work perfectly, but this one totally did. The excitement level was very high when we saw these 3 perfect bars. Taking a closer look at them, copper has some black staining on it which we can't really tell what it is. It's not the graphite mold since the markings are on top, so if you know, we would love to know as well. Leave us a comment. A quick touch up with a file seems to remove it very easily though, so we'll clean it up in a moment. Looking at the brass, it also looks really good, but it does have some silver looking discoloration. That's probably foreign material introduced by random things that we were throwing into the molten pool. As per the aluminum, it looked like a nice loaf of bread. Aluminum has a very low melting temperature, so it wasn't really a surprise that it melted. The experiment was really more focused on the copper. So now let's go surface these on a CNC mill. We just placed them in a vise using parallels to keep them all at the same height, and we got straight to work. The vibrations made the camera extremely shaky, so we took it off. The final results looked awesome, but nothing's ever quite perfect, is it? Looking at the aluminum, we seem to have all these tiny bubbles inside, and we have no idea why. We're not sure what we did that may have caused this. A similar thing happened here with brass, although it seems very dense and solid aside from the few scratch marks. And copper was probably the best. It's very solid, and look at that mirror finish. You can even make out my fingerprints in the reflection. But we still have no idea what's causing these massive air gaps. Our inexperienced assumption is that we are casting too slowly and would love to cast proper solid bars if anyone knows the trick. If you know what's going on, don't hesitate to reach out in the comments. We respond to every one of our subscribers. Speaking of which, we have nothing to do with these bars anymore, so we're giving them out to one random subscriber. Get on board by hitting the subscribe button right now. Out of curiosity, we wanted to weigh these bars to determine their approximate scrap value. We started with copper weighing in at 444 grams. This gives it a scrap value of around $4.56. Next was brass weighing 422 grams, giving it a current scrap value of approximately $3.37. Lastly, we weighed the aluminum at 133 grams, which is worth only 41 cents in scrap. Overall, the total value of these three bars is $8.34. By the way, if you like this funny t-shirt I'm wearing, make sure to check out the new merch on our website. Your support directly funds our other machine-related videos. Thanks for watching. We'll see you next time.